Okay, now you should be able to hear me. Everybody hear me okay? So there is a delay between what you see on the screen and like when I type something, you'll hear me talk about it 20 seconds later, because there is a slight delay. So if you have a question, I'm constantly watching that. So if you have one, just type it into the comment box there, and then we can address it. Okay? Excuse me. I keep these unlisted, so nobody else should have these links to my YouTube channel. Okay? I carve out this space just for you, so that we can, we don't have the public jumping in here like, ooh, I wonder what this is, and then, they're taking over the comments. Okay, so I mod. I had a Twitch channel, and I also mod for. Well, I modded Twitch for a little while, and then I still mod two YouTube channels and a couple of Facebook groups. So, yeah, I'm well aware of what happens when people just sort of join in, and it can get pretty ugly when you just open things up to the public. You just never know. So, oh my goodness, and I spelled here H-E-R-E. What is wrong with me? Don't show that to my wife. We love to give each other heck over the way we spell things. We have a picture up on the wall, and it says there, and it has all three spellings of there, because that's one of our pet peeves. But anyway, so this is my bread and butter. I like being over here on YouTube. I'm comfortable here. I like using my OBS software, and I can get to things very quickly. I've got my HD camera set up, and so, like this is another view where I'm going to go to my PowerPoint, and then I can switch over to my, a browser if we need to look at something here. And I can also go to my whiteboard. So that's an easel I built for my kids. And so it's easy for me to just come over here, and like when we do our, we're going to be doing some calculations. And so, obviously this was for them, and I made it small, but I screwed it up here to my my assembly workbench, or my assembly bench. And so yeah, I'll be utilizing this some. When we start getting into more of the programming stuff in Quartus, then it's not going to be as crucial that I use this. But it's nice to be able to have this for whatever I need it. Okay, and I've got both my box lights on it, so it should be really visible. I've worked really hard the last couple months on my setup here. So, but anyway, let's go ahead and get into chapter 1. And by the way, this is, if you go to Canvas, you go to the modules, that's where all the PowerPoints are. And I always use the Clites. Okay, there's a lot of times, no, the Clites PowerPoints are like 90 slides long. I don't go through every single one of them. I know which ones that I can sort of move past, and which ones I need to really focus on. Okay, so yeah. Again, if you have any questions, just go ahead and type them into the box. All right, and I'll check back every so often. But let me go ahead and get into the PowerPoint here. Okay, so this is chapter 1. And so I usually don't cover the objectives. I usually just go right into what our discussion is going to be about, okay? And so actually, if I go to the syllabus, I meant to do that. I meant to have it pulled up. Let me pull it up real quick. Just take me 2 seconds. There it is. And I'm going to scroll all the way down to the bottom as soon as it loads. Well, maybe. It just disappeared on me. Let's try this again. Open. So in this first session today, we're not even going to cover all of Chapter 1. We're going to go all the way up until BCD. So we're going to learn all of what I call the weighted number systems, and then we'll talk next time about the unweighted systems. Now, depending on how quickly this goes, I may just end up running right into this. I don't know. We'll see. There's no reason for me to do that, though. I've thought about, for this summer session, just sticking to, do Chapter 1 in one session, then do Chapter 2 in another session, then Chapter 3 in another session. But I think we'll be okay doing it this way. There's going to be enough for you to do after 1.9, believe me, okay? So anyway, I just wanted to point that out. All right, so let's get back in here. And so you may have heard these two terms, digital and analog, okay? Digital, we use what's called discrete items, all right? Anything that's discrete is typically something that can be represented with on, off, yes, no, true, false, 0, 1. All those things in the digital world mean exactly the same thing, respectively, okay? For analog, the sound of my voice right now, the temperature outside, if you want to think about it in terms of music, old wax records are continuous analog recordings, right? All of this digital music that you stream is all sampled. No matter how fast it's sampled and how close it sounds to the original, it is still not the original. There are still gaps no matter how quickly you do something, okay? Whereas an analog signal, which is how our television and radio used to be broadcast, right? That's continuous. It's a constant signal. The sound of my voice is a constant signal. It has inflection, it has amplitude, and it changes in frequency, but it's continuous. There's no gaps in it. Now for you, technically there is, because I'm going through a digital device. It's getting transmitted digitally, and then it's turned back into an analog signal through either your headphones or your speakers on your laptop. So what you're hearing right this second is a sampled version, right? Because you're on the other end. But if we were in class, see, I'm so primed to you standing right in front of me when I say things that now I have to think about, well, you're not in front of me. You're actually in the digital portal. And so everything you hear from me is not the way you would hear it if you were to stand in front of me. You can tell when something is a recording and when something is, in person, because that sound then bounces off everything in the room continuously, right? It's a different experience. So temperature, pressure, velocity, there's an air pressure in your room right now, wherever you're sitting. It's probably somewhere right around 14.7 pounds per square inch. If you're in an apartment and you're upstairs, you probably have a little bit less, right? Because as you go higher and higher, even 30 feet into the air, that's got a different air pressure than where you're standing right now, okay? And if you go up high enough in the air, then as you go up to space and there's no air pressure at all. It's just a vacuum. So right now we have 14.7 pounds per square inch constantly, analogly, if you will, bearing down on this. And that's a good thing, because if our bodies were to not have that pressure to act against, then we would explode from the inside out, right? That pressure keeps everything internal in our bodies, which is a good thing. So anyway, we're talking about two completely different worlds. The sampled worlds, where everything's represented with ones and zeros or on-off states, versus the actual amplitude over time for analog signals. Okay. So what are some of the benefits of using digital signals? Well, if you're only dealing in ones and zeros, it's less likely that you will have noise that interferes, okay? Digital systems are typically very stable. They're not susceptible, in most cases, if it's designed correctly, you can get rid of some of that electromagnetic noise. And you can also program your circuit to deal with the fact that there might be some noise on there, whereas most analog systems are susceptible to that type of stuff. If you remember, before they started doing phones, like if you ever had, I had a dial-up phone on my wall when I grew up. I'm 41 years old as of yesterday, okay? So I grew up with a dial-up phone on my wall, and it was analog, and if there was some static on the line, you would hear it. it would sound kind of staticky, right? And that's because, it wasn't a clean connection, and there was interference that was getting on the lines and then being transmitted in each direction. Whereas a digital system, what happens when your digital satellite goes out? Do you have a fuzzy picture and then you can adjust the rabbit ears? No. It pixelates and goes black. It's either on or it's off, right? That middle pixelated, green, only half the squares are showing. That's the kind of that's the kind of fuzz that you see in digital systems, okay? There is no adjusting the rabbit ears, so to speak. I mean, I know that the digital systems do have rabbit ears to try to grab the signal, but it's not like you're getting rid of the static. You're just getting a cleaner reception to the signal, okay? So anyway, so that's a big reason why. And digital systems are smaller in size. If we had to use analog components, I guess transistors are technically analog components, so we could do it. But digital systems are very, very small, and they're very, very quick and reliable, okay? So there's a lot of benefits to it. Now, when it comes down to things like music, there are purists who refuse to use anything digital and say that the only way that you can get a good sound is if everything is analog, okay? And I've heard artists say that, and then they turn around and put their stuff on iTunes. So, I mean, you can't get away from it at this point. We don't even buy CDs anymore, I still have my cassette tapes somewhere. I can't find them, but I still have them. So anyway, it says, are there any problems associated with digital systems? Well, they're reliant on having a certain voltage, and if they don't have that certain voltage, then the stuff won't turn on. So, just depends on the application. But in most cases, it's usually a benefit. When you start getting into audio stuff, I realize it's different. But for most systems, they greatly benefit from a reliable digital system where, like now instead of physical timers wearing out, you can have a timer internal in the software or in the hardware where you don't have a rotating mechanism that's doing your timing. You have digital clocks that are doing your timing. All right, so that's not going to wear out the same way that a mechanical timer would, for say. Some of you may have a watch like you see on the left. I don't have any watch at all because I have not since I got a smartphone anyway. But anyway, this is the analog dial, right? It's continuously running, right? Some of them do a clock, 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 and so the seconds arm will do 1 second at a time, right? But it's still got mechanical gears and electrical stuff going on there. It's not digital, okay? And if they're really, really expensive, then they have, this thing is just it's perfectly timed to make a circle in 60 seconds. And so it never stops, all right? That's still a mechanical and an analog motion, okay? Smooth, continuous changes that you can track. With digital, this is 1127, or I'm sorry, this is 832. It's probably the date of 1127, but this is 832, okay? It's not 832 in a couple of seconds like you could show here with these three faces, three dials. It's 832. And this 2 is actually just 1, 2, 3, 4, 5 LEDs that are turned on. You see that? To make up the number 2, we use what's called a 7-segment display, which we'll talk about. You can see the segment break up here easier on the 7, right? For a 7, you need 1, 2, 3 segments turned on. For the number 2, you need 1, 2, 3, 4, 5 segments. And for the number 8, you got to have them all. All 7 have to be turned on to make a number 8. Okay? So it's a different approach to giving someone information, whereas here, I have to know something about this dial to understand how it works. Whereas here, I can just say 8:32, and then, okay, that's what time it is, right? I don't have to find the shorthand and the longhand. So again, there's benefits to it, right? Certainly, in the world of streaming and videos, the ability to stream videos over, in high definition from some server somewhere is a great thing. We can now carry our entire music library in our phones, as Steve Jobs wanted us to do, Oh, excuse me. I had to take a drink. It is hot out here. So, most of this stuff is review for you, right? I mean, you may not be my age, but you understand the difference between analog and digital, right? Here we're talking about stuff that's on or off. Here we're talking about a mechanical or electromechanical device or a source of communication or whatever. Okay, it's continuous. It doesn't stop. Let's see here. So in 122, that's where we talk about how to do these type of conversions, where you sample the analog signal at a certain point and convert that amplitude into a digital number, right? And so then if it gets up to this point, right, it crosses this threshold, that voltage equals the next binary count. And then this voltage represents the next binary count. So you can still represent an analog signal, you just have to do it with binary numbers. Okay? I love this. And I always think of like Patsy Cline or something, like this is a drawing from the 1950s or something. But anyway, so you take a person who has analog communication coming out of their mouth into an analog microphone that goes into a CD recorder, right? And so you take that analog signal, you convert it to digital into ones and zeros. On a CD, it's called pits and valleys, okay? And so on the bottom side of the CD is just a bunch of pits and valleys that represent ones and zeros, okay? Then you take that digital media, put it into a CD player. It takes that digital information, converts it back into an analog signal, amplifies it, and then that's what comes out of the speaker, okay? So it goes into digital, you record it onto digital, and then you put it into a CD player, and it comes back out analog, okay? But if you were going to do this with cassette tapes, you'd have to record onto a cassette tape, same thing, then you'd have to take it over to a cassette player. It's just there wouldn't be any digital conversion, it would be all analog, okay? But if you're old enough to remember cassette tapes, the worst thing about them was the tape hiss. And if you played it over and over and over and over, like some of us used to do, your tape would start to what we would call wear out. So, over time, it starts to, the sound sounds like it's receding into the speaker. It's not as loud anymore, and then you hear this over the top of it because you've worn out the tape, and so you'd have to go buy a new one. Whereas CDs sort of solve that. But then the CDs had the problem of scratching it, and then when the laser tries to read those pits and valleys, it gets diverted somewhere else, and then it doesn't work. So now we just stream it all. And now what happens, the only way we get anything, if we have any issues, it's because our internet goes down or our internet gets slowed down or something like that, right? So this is something I addressed before. So digital systems are immune to analog noise, and that's anything that can get on the line, that on an analog signal you would hear, okay? Because it's going to allow that amplitude oscillation to come through as in the form of static noise, typically, okay? Now, if we're talking about something that is on versus something that's off, if I'm bouncing a couple of 100 millivolt here, that's not enough to cross the threshold to make a high. So even though there's noise here, I'm still considered a low down here. And the same thing up here. If I'm high currently and I have a little bit of noise, even let's give myself 700 millivolts of oscillation here. That's still not enough to be registered as a low. So you've got, it's either the one thing or it's the other. Here, you have an oscillating amplitude that gets, passed right through into the speaker. Okay? Any questions so far? I'll type this in so you'll see it 20 seconds from now. Any questions? Oh boy. The sweat is rolling down my face. Okay. It says energy technicians must keep track of the efficiency of their energy collection systems, like solar, wind. Those are big deals these days, right? Solar power, wind power, electric vehicles. My dude Elon Musk with Tesla and all the stuff that he's doing in that area. You know, if you're going to create a system like that, if you're going to rely on solar being the energy source, well, then you probably need to put it somewhere where there's sun. And you probably don't want to put a windmill somewhere where there's no wind. So, you know, the other thing is even if you are going to try to create these systems, the main thing is those are all analog quantities. And so they have to be digitized before you can even get any computer assistance. So that goes for, you know, if you have a temperature device, if you can, you know, temperature devices like thermocouples and RTDs and thermistors and things like that, typically you have a thermistor and your thermostat at home. So, you know, the thing that you adjust to increase the temperature and turn the heater on, or decrease the temperature and turn the air conditioner on, that unit, the thermostat unit, has a thermistor inside of it, okay? And so all that's doing is when I believe the thermistor operates off resistance. And so there's some formula that when the temperature changes, the resistance output of the thermistor changes. And it's a proportional change to the temperature. You just have to know what that is. Same thing with thermocouples. You take two dissimilar metals and you put them together on one end. They produce a proportional millivolt output, believe it or not, based on what the temperature is. And so you can take that analog voltage, convert it into something that we can utilize. Like if you have a thermocouple and you put it into a temperature display, that's what's happening internally. It's taking that analog voltage. It knows where it's supposed to be scaled. Maybe it's a 0 to 5 volt output or something, whatever the device is. And then you can scale what that converts to in terms of temperature. And then you can display that on a 7-segment display. Okay? Let's go back here and see if there no questions so far. Let's keep rolling. And this is a very 30,000-foot view of, oh, hang on a second, it's raining and I've got concrete sitting 2 feet from my door. Hang on, I really apologize. Hang on 2 seconds here. Oops. Oh my goodness, this is heavy. Just need to get it here in my garage. Can't believe I did that. Sorry about this. All right, that's good enough. Good enough for now anyway. Okay, sorry about that. Hopefully it'll cool off now though. But this is the 30,000-foot view of the solar radiation data logger system. So you got all these solar panels that get multiplexed into a system. You take the analog output, convert it into a digital storage mechanism so that you can keep track of how much you're taking in. And then you can shift that out to a USB, and then you can then store it, you know, like on a USB drive, or you can connect it to another computer, okay? All right. So, before we deep dive into doing any kind of analog to digital signal conversion, we got to take it all the way down to, what do you mean by 10? What do you mean by the number 23? You know, we kind of have to step back for a second, because I realize that we all utilize base 10 numbering. This is how all calculations are performed, okay, in terms of mathematics. Base 10. That means there are 10 possible digits. 0 through 9. There are no other digits. There are bigger numbers, like 123, but that's made out of a 1, a 2, and a 3. There are only 10 digits, hence base 10. Okay? This is the number system you grew up with, and that's regardless of where you grew up, right? So if I take $10 plus $10, that's $20. If I take 15 euro plus 20 euro, that's 35 euro, right? Everything's based on this base 10 number system, okay? And what we mean by that is, when we say a weighting factor, this is called a weighted number system. In other words, each digit's place has a certain weighted value attached to it. Okay, so I'm going to turn over to my camera real quick to illustrate. So if I have the number 629, okay, 629. So what I mean by a weighted system is we call this the ones place, right? We call this the tens place. We call this the 100s place, right? But what does that actually mean? 629. That means that the weighted value of this digit is, because it's base 10, 10 to the first. The weighted value of this digit is, I'm sorry, this is 10 to the 0. This is 10 to the first. And this one is 10 to the second. Okay? What is 10 to the 0? It's 1. The ones place. What's 10 to the first? 10. The tens place. What is 10 squared? 100, right? 10 times 10. So that's the 100s place. All right? So really what we mean, and we don't think about it like this, but we're really saying it's 6 times 100 plus 2 times 10 plus 9 times 1, right? Add all that together, you get 629, right? Because this is going to give you 600 plus 20 plus 9. And you might think, okay, that's like trying to explain the alphabet to a kid. I understand. But I'm trying to get you to understand how you have to start thinking about the digits of a number. Okay, you can no longer just say 629, because I'm going to say, okay, 629 in BCD. Is that 629 in base 10? Is that 629 in hexadecimal? It can't be binary and it can't be octal, because those use 0 and 1 and the other one uses 0 through 7. So 9 is not a digit in octal. But this could be decimal, this could be BCD, this could be hex. So I'm going to start from now on telling you what base my number is when I show it to you. This is 629 base 10. Okay? If I had 629 BCD, notice the difference in how I say it. I'm allowed to say 629. Okay? Here I say 629 in BCD. Okay? So anything other than decimal, I will never use 100, you know, what we use for base. So if this was 629 hex, that's what I would say. I would say 629 hex. I would not say 629. 600 implies base 10. Okay? So hopefully we can make that distinction. All right. So, weighting factor of 10 in each digit, 10 to the 0, 10 to the first, 10 squared, however many numbers that you have. Okay? Any questions on this so far? Okay. Just checking back here on, I don't think anybody has any questions so far. Okay, so let's keep going. All right, so now we're going to talk about base 2. And this is the base for which all computer language is run, because it's all binary. Sorry, I had to take another drink. I am sweating out here. So anyway, base 2. Only possible digits are 0 and 1. Hence, base 2. Remember, in base 10, we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different digits that we use. In binary, we only use 0 and 1, so that's 2. That's why it's base 2. So each digit in binary has a weighting factor of 2 this time. Okay? So, let me come back to the board here. And I will erase what I had. So for binary, base 2. Okay. If I had 0, 1, 1, 0, okay, and this is base 2, okay? The rightmost digit, which is what we call the least significant bit, or the, in base 10, if I have 629 base 10, that's the least significant digit, right? And that's the most significant digit. Same principle applies for binary. This is your least significant bit, and this one is your most significant bit. It's the one that's out in front. Okay, so just some terminology to learn. This weighted value is based on base 2, so this is 2 to the 0. The next digit, 2 to the 1, 2 squared, 2 cubed. Okay, so what does that equate to? Well, that's 2 to the 0 is 1, 2 to the first is 2, 2 squared is 4, 2 to the third is 8. Okay, so as we increase the number of bits in our binary number, you just keep multiplying by 2. The next one is 16, and then 32, 64, 128, 512, or 256, 512, right? So you could have a 16-bit number, and you just keep, each digit is weighted even more than the last one, twice as much. So let's look at this case here. If I'm going to figure out how to convert from binary to decimal, so this is a binary to decimal conversion. So I'm going from base 2 to base 10. All I do is multiplication. I do my weighted multiplication here. So I have 8 times 0 plus 4 times 1 plus 2 times 1 plus 1 times 0. Okay? This gives me 0 plus 4 plus 2 plus 0. So that equals 6. Okay? So 0, 1, 1, 0 in binary is the same as 6 in decimal. Okay? And use that method for all binary to decimal conversions. Okay? Let me do one more. I have to screw down those back legs too. Okay, let's take 11011 base 2. Okay, everybody can see that? So again, this is, I'm going to go ahead and erase this up here. Binary base 2. We've got 2 to the 0, 2 to the first, 2 squared, 2 cubed, 2 to the fourth. So we've got 1, 2, 4, 8, 16. Okay? Now we do our weighted multiplication. So I've got 16 times 1 plus 8 times 1 plus 4 times 0 plus 2 times 1 plus 1 times 1. Okay? And so we've got 16 plus 8 plus 0 plus 2 plus 1. So this gives us 24. This gives us 3. I think the answer is 27. Okay? Make sense? Okay. I'm going to do another one here. I want you to try it on your own. How about 10110 base 2? And I want you to go from binary to decimal. See if you can jot that down on paper real quick. Anybody get it? Okay, you still may be working on it. So Steve's the first in with 22. Let's see. 2 to the 0, 2 to the first, 2 squared, 2 to the third, 2 to the fourth. So we've got 1, 2, 4, 8, 16. So that looks like 16 times 1. I'm not going to write the zeros on this one. 8 times 0, 4 times 1, plus 2 times 1 plus 0. So that looks like, yep, I think so. So 10110 in binary is 22 in base 10 decimal. Okay, very good. John got it too? All right. All right, let's go back over here. Now, you'll see what it says here. It says digit times the weighting factor. That's what we just did. What if you want to go the other way? What if you want to go from decimal to binary? Okay, let's go ahead and look at that. We're going to use something called successive division. Okay, let me go ahead and get switched back over here. Okay, so now I want to go from decimal to binary. So I'm going to choose the number 43. Okay, so now I want to convert that into binary. All right. So the easiest way I've found to do this is to kind of set yourself up a little table. It's not really a table, but it's something that you can fill in. And this is how I do it. So I know that if I go by 2 in my head, I do 16, 32, 64. So I just need to go up to the 32nd place, I think, because I don't need 64. So I can go, so 2 to the 0, 2 to the first, 2 squared, 2 to the third, 2 to the fourth, 2 to the fifth. Okay? And this is 1, 2, 4, 8, 16, 32. Whoops. 32, not 33. Okay. So what I'm going to do is, I say, if I had this, let me go ahead and put it on here just so I can say no to the question. Okay, there's the 6th position right there. It's actually the 7th position, but the 6th bit. That would be the 0th bit. So I asked the question, does 64 go into 43? How many times? 0. So that gets a 0. Okay? So next I ask, okay, how many times does 32 go into 43? And the answer is 1 time. Okay, so I need one of those. Now I subtract it. I'm left with 11. Okay? How many times does 16 now go in? Now this is, forget about that. We're now down to this number. Does 16 go into 11? No, 0 times, right? What about 8? How many times does 8 go into 11? 1 time. So we need one of those. Now we'll subtract the 8, and we're left with 3. How many times does 4 go into 3? 0 times. How many times does 2 go into 3? 1 time. So now 2 into 3 goes 1 time. I'm left with 1. How many times does 1 go into 1? 1 time. And finally I'm at 0. So I'm not going to include that front number there, or for that front digit. But 43 in decimal is the same thing as 101011 in binary. Okay? Any questions on that? Yep, John got it. 101011. Okay? All right, I'm going to do another one real quick, and I want you to try to do it on your own. And then I'll step in and solve it. how about the number 79, the year I was born? Okay, I want you to go from decimal to binary. Okay, and I'm going to go ahead and set this up over here, and I'll do it one more time. I'll do the 2's over here. 2 to the 0, 2 to the first, 2 squared, 2 to the third, 2 to the fourth, 2 to the fifth, 2 to the sixth. So we've got 1, 2, 4, 8, 16, 32, 64. 2 to the seventh, if you do a full byte, is 128. So you could write that one down too. Okay? Go ahead and see if you can do this one. So John says 1001111. All right, well, let's see what happens. Okay. The first question I will ask is, how many times does 128 go into 79? The answer is 0. But the next one, how many times does 64 go into 79? 1 time. So I subtract it, and I'm left with 15. How many times does 32 go into 15? 0 times. How many times does 16 go into 15? 0 times. How many times does 8 go into 15? It goes in once. I'm left with 7. Okay? How many times does 8, I'm sorry, that was a 1 here. How many times does 4 go into 7? 1 time. I'm left with 3. 1 time. How many times does 2 go into 3? This is a long one. Goes 1 time. I'm left with 1. How many times does 1 go into 1? 1 time. 1 into 1 goes once. I'm left with 0 finally. So, John is correct that 79 in decimal converts to 1001111 in binary. Okay? How'd everybody do here? Very good. Very, very good. We're all on the same page so far. All right. Okay, well, let's keep going then. Let's keep the fun rolling as the sweat is just drenching me. Okay, so there we go. That's our decimal to binary, and that's called successive division. Is what we just did. Okay, the next one we're going to talk about is called octal, and octal is base 8. The reason why base 8 is something that we study along with hex is that they're both powers of 2. So 2 to the 0 is our binary. 2 squared would be base 4. 2 to the third power is base 8. And 2 to the fourth power is base 16. So that's why we specify octal and hex. Okay? It's not just random that we picked those 2 base numbering systems and decided to teach you about them. It's because of the way that computers are constructed and how they utilize information and how they transfer bytes of information and things like that. So, you can see here, everything is the same 0 through 7. Okay, it's just that because they're only using 8, the first 8 digits, 0 through 7, that's 1, 2, 3, 4, 5, 6, 7, 8. That's 8 digits. We don't use 8 and 9 here, even though it's base 8. Okay? So decimal, we just keep counting like you've always counted since you were young, right? Binary, you eventually will be able to look at 111 and know that's a 7. You eventually look at a 1001 and know that's a 9. Just because you're going to do this stuff so much over and over that you will start to pick up the patterns, and then you'll be able to count in binary in your head, okay? That's a fun trick when you go to a dinner party. Hey, guess what? I can count in binary. Anybody want to hear? 0, 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 0, 0. You know, gets pretty old pretty quick, right? But I'm impressed if you can do it. So because we are on base 8, okay, that's what the weighted value is of each digit. It's just that simple, okay? So I'm going to go ahead and switch over here. If I can get to my OBS and come back to the board and erase this. So much for letting a breeze come in here. It's all humid. All right. This was a lot more comfortable in the spring. Oh, let's take the number 27. Okay? So I'm going to take the number 27 in octal, and I want to go from octal to decimal. Okay? We use the same method as we did before, where we weight each digit, and then we do a multiplication and addition to add it up to see how we get to the decimal value. Okay? So this one is 8 to the 0. This one is 8 to the 1, 8 to the first. This one is 1. This one is 8. Okay? So this one you got to be a little bit more careful because you're not just dealing with ones and zeros. So now we have 8 times 2 plus 1 times 7. So we've got 16 plus 7, 23. Okay? So the octal and the decimal numbers are not light years away like you might think, okay? Because it's only, we're only not counting the 8 and the 9. We're going, you can see, if I switch over here real quick, you can see there it goes 0, 1, 2, 3, 4, 5, 6, 7, and then I would say that that's 1, 0, 1, 1, 1, 2. That is not 10, 11, and 12. Those are very specific terms for those values in the decimal system. That is 1, 0, and what I'm talking about is, let's see here. Get back over to the PowerPoint so you can see my cursor. So this is 1, 0 in octal. This is 1, 1 in octal. This is 10. This is 1, 0 in octal. Okay, so you see the difference? This is not 1,000 in binary. This is 1, 0, 0, 0 in binary. Okay, so I'll keep stressing that point. Okay, let's head back over to the board. And now I'm going to have you do one. And I'm going to do, let's step it up a little bit. How about 4, 0, 2, 9 in octal? Convert that to decimal. Okay? And I'll go ahead and give you a hint up here. This is 8 to the 0, 8 to the first, 8 squared, 8 cubed. So we've got 1, 8, 64, and then, what is that, 472? Geez, now I got to do it on a calculator. $64 times 8. 512. Geez, John. 472. Whoa, that's so ridiculous. 512. All right, and so, yeah, so that should help. That's going to be a fairly big number. Oh. I use my calculator for my calculations. I use my brain to memorize concepts and how to do it. But if you ever take Professor Atkins, he has got a ton of this stuff, you know, committed to memory just from using it for so long. So like he can tell you what the decimal is for, you could probably give him what, 7/15, and he'll give you you know, an answer that's close within 3 decimals. All right, let's double check over here. So Steve is saying 2073, 2073. All right, well, let's see. I'm gonna actually have to get my calculator out here and play along. It's got to be like 70% humidity right now. Okay, so we've got 512 times 4. So that's what, 1,048, plus 64 times 0, which is 0, plus 8 times 2, plus 9 times 1. So, is that 5? No, that's 2048, right? Because that's 2,000, yeah. So 2048 plus 16 plus 9, so that's 25. So 2048 plus 25, 2073. And that is 2073 in decimal. $2,073 in decimal. Okay, I think that's what you said, Steve, right? Yep, 2073. Very good, very good. All right, so we're all following along here. I'm impressed. Let's do this. Okay. Well, if we're gonna go one way, let's now go from decimal to octal. Okay, and let's take the number, let's go with 3,622 in decimal. Okay, and we want to convert that into octal. We're going to do the same thing that we did before. It's called successive division. Okay. So what were our numbers here? We had 512, we had 64, we had 8, and we had 1, right? That represents 8 to the 0, 8 to the first, 8 squared, 8 to the third, okay? So I'm not going to go to the next one after this, okay, because I think that's over 4,000, right? Because 8 times the 5 would be something over 4,000. This is under 4, so I think we're okay where we're at here. So the first question is, how many times does 512 go into, 3622? Okay, well, the actual question you should ask is, how many whole times? Because you're not worried about the decimal. You just want to know how many whole times does it go in, and then you get the remainder from there. So 3622 divided by 512 goes in there 7 whole times. Okay? So 7 times 512 gives us 3,584. I subtract that from 3622, and I get 38. Okay? So I have a 7 here, right? How many times does 64 now go into 38? 0 times. Okay? How many times does 8 go into 38? Okay, that's going to go what? 4 times. Jeez. So it goes in 4 times. That leaves us with 6. How many times does 1 go into 6? Goes 6 times. We're left with 0. So 7046 in octal is what we get for 3622 in decimal. Okay? Yep, and somebody had it there. 7046. Very good. All right. So you can see this is kind of this is all really the only calculations that you'll be doing in this type of class, okay? Because the whole class is after we get done with these conversions and things and number systems, then we start going into gate logic and things like that. So enjoy it while you can if you're a math nerd, because this is about as good as it gets for this class, okay? But I feel like that's you're using either one or the other for most of these calculations, okay? So that's decimal to octal. I want to do one more with octal real quick. Okay. I want to go from octal to binary. Okay? So I'm going to choose the number O. Oh, geez, what should we do? We should do 1, 0, 7 in octal. Okay? That'll give us a nice representation here. Okay? So here's what's great about going from octal to binary or binary to octal. All you need to do is, if I pull it up here, is you just need to go back to this right here, okay? You're doing a direct conversion for each digit. So what I have up here is 107 in octal. That means for the number 1 in binary, the 3-digit representation is 001. So mine's going to be 001, 000, and then 111. That's going to be my binary equivalent. Okay, so when we go octal to binary or binary to octal, we're worried about grouping those bits into groups of 3. Okay, so watch how I do this. The 3-digit binary representation of 1 is 001. The 3-digit representation of 0, 000. The 3-digit representation of 7, 111. So if I knock off the leading 2 zeros, I have 1000, 111 in binary. Okay? Super quick. Don't even have to do any calculations. You just have to use that chart and do the direct conversion for each digit. Okay? Let's go the other way. Now, we want to go from binary to octal. Okay? So I'm going to choose the number 110101111001. Okay, I didn't count how many I have, so we'll see here. So I start from my least significant bit over here, and I just start doing groups of 3. There's a group of 3. You always have to start from the least significant bit when you do this. There's a group of 3. There's a group of 3. Now, there's a leading 0 out here that makes this able to convert. Okay? I then go back to this chart right here. Okay? So, what is 001 in octal? It's 1. What's 111? 7. What's 010? 2. What's 011? 3. So this is 3271 in octal is the same thing as this big long thing in binary. Okay? Let's see what we got here on the chat. Somebody type it? Nope. Am I getting to it? All right. Now, I'm going to have you do a couple. And I won't make them as long here because I feel like you're on board, so we don't need to do too many examples of each one unless you want me to. So for the first one, I want you to take 7-3 in octal and go to binary. And then I want you to take 11011 in binary and convert it to octal. Okay? Go ahead and do that real quick. Okay, so Steve's come up with 111011 for the first one. And 33 for the second one. Okay, well, 33. 3-3 for the second one. Okay, well, let's see what happened. All right. So for the first one, the 7 directly converts into 111. The 3 directly converts into 011. So that's the binary equivalent. Okay, I'm just doing a direct conversion from the 7 to the 3-digit binary equivalent and the 3 into a 3-digit binary equivalent. Okay, down here, here's a group of 3. Okay, I have to put a leading 0 out here to make this a group of 3. But what's my direct conversion? 011 is 3. 011 is 3. So that is 3, 3 in octal. So 011, or I'm sorry, 11011 in binary is 3, 3 in octal. Okay, very good, very good. We're cruising right along here. David said, "Go, Steve." All right. Let's see here. As I towel myself off. Whew. All right. So we just did all of those. Okay. So the last one we're going to talk about here is the hexadecimal number system. This is base 16, and this is also why sometimes you'll see a number represented as like 4F or E5 or something like that, okay? That's utilizing, because we're in our Western numbering system, 0 through 9, those are our only numeric digits, right? So if you have base 16, well, that's 0 through 15. So how do you represent the numbers 1, 0, 1, 1, 10, 11, 12, 13, 14, 15? Well, you can just replace them with the first 6 letters of the alphabet. Fair enough, okay? So we are going to do all 4 the different variations. We're going to go hex to decimal, decimal to hex, and we're also going to go hex to binary and binary to hex, okay? And if you want to go from octal to hex, the easiest way to do it is just to convert it into binary first, and then you're just doing the same thing where you're grouping, and I'll show that to you here shortly, okay? So you may be wondering, here I'm throwing around all these terms, right? And I'm sure you've heard the word bit before, and I'm sure you've heard the word byte before, but did you know there's one in between called a nibble? So if you have one single bit that can store a 1 or a 0, that's called a bit, right? I guess if you're a little bit more hungry and you have 4 bits, you have a nibble, okay? And then if you have 8 bits, well, that's a bigger byte, right? And then here's where they lose me. Does anybody know what 16 bits are called? I'm going to type it here. Anybody know what 16 bits are called? I'll wait for an answer here since I typed it. So far we've got bit, that's one single, and then we have a nibble, which is 4 bits, and then we have 8, which is a byte. So we're sticking with the food and eating. Gulp or a hexit? No, do you know what it's called? It's called a word. It's called a word. Okay? I don't understand that. Why didn't they do gulp or munch or, something? If you're going to stick with that, why do you go from byte to word? Okay? So I've never gotten a good answer for that. But anyway, here's what it is. Okay? All right. So let's go ahead and look at the next slide here. And here's where we go with the hexadecimal number system. Okay? This requires 4 bits to get through one cycle of 0 through 15 to go through all 4 bits here. Okay, from 000 to 1111. Then it starts to repeat. Okay, so instead of going 0 through 9 and then starting to repeat like base 10, or 0 through 7 and starting to repeat like base 8, or starting to on 0 and 1 for binary, we go all the way up to 15, and then we recycle. Okay, so that 10 is represented by A, and then B, C, D, E, and F, and then 1 0 in hex is the same thing as 16 in decimal. Okay, so this is a great chart to have. There's another one that's even better that I would want you to write down. But anyway, I'll point that out next time that we have our discussion here, okay? But this is the number system. So since we are in hex, and because we have base 16, all right, each of those digits is weighted by 16. So now we have 16 to the 0 and 16 to the 1 and 16 squared. Well, that ratchets up the count pretty darn quick because we have a base of 16. So, you can convert a very long, and this is why it's done, you can convert a very long binary number into a 2-digit hex number. Okay? All right. Well, let's go ahead and do some conversions here. Get back to the board. I find my marker. All right. So if I have, let's make it E5 in hex. Okay. This digit is 16 to the 0. This digit is 16 to the first. So that's 1 and 16. Okay. Now remember, when you go to do this, if you do have a letter, you're just going to use the decimal equivalent in this calculation. So I've got, if I'm going to convert from hex, I'm going to go ahead and put this up here so when you go back to look at it later, you can easily spot it. Hexadecimal to decimal. And so we're going to have 16 times E is 14 plus 1 times 5. Let me get my calculator out here. So 16 times 14 plus 5, 229. So 229 in decimal is the same thing as E5 in hexadecimal. Okay? Okay, Steve says, I got to get ready for work, but I'll keep the lecture on. No problem. Like I said, because we had to do all the housekeeping stuff at the front today, that's why this is going on so long, okay? Normally, we'll just get right to it at 10 after. So, no problem, no problem. Okay, I don't see any other questions here. So let me get back to the board. Okay. So let's do another one. Let's do F5C in hexadecimal. So this is 1, 16, and 16 squared, 256. Okay. So now I've got, if I'm going to convert this to decimal, 256 times F is 15 plus 16 times 5 plus 1 times C is 13, right? Wait, A, B, C, D. So C is 12, right? Isn't that what I said? C12? D13? Yeah, because it's 1 off of D12. That's how I always used to remember it. I try to do mnemonic devices for that stuff. So that should be 12. So 1 times 12. Okay? So 256 times 15 is 3,840 plus 16 times 5 is 80 plus 1 times 12 is 12. So we've got 3,840 plus essentially 92 there. So 3932 base 10. So F5C in hex is 3932 in decimal. Okay. All right. Looks like everybody's on board. Now let's go the other way. Okay. So now we're going to go from decimal to hex. Okay. So let's choose the number 2,361. Okay. So that is decimal. So for my hex, I'll set it up the same way again. So I've got 16 to the 0, 16 to the first, 16 squared, 16 cubed, just so we can put up what that gigantic number is. 16 cubed, 4096, and what did we say? 16 squared was 256, and 16, I'm sorry, yeah, 16 and then 1. Okay. So how many times does 4096 go into 2361? 0 times. How many times does 256, how many whole times does 256 go into 2361? Well, if we take 2361 divided by 256, we get 9 whole times. And so 9 times 256 gives us 2304, which is what? 55? That's not right. That's going to be 57, not 55. There's a breeze. Whew. So 57. So it goes 9 times into this digit. Okay. What about 16? How many times does 16 go into 57? So 57 divided by 16 goes in there 3 whole times, and that gives us 48. So 3 here. So now that's left us with 9. And then how many times does 1 go into 9? 9. So 939 in hex is the same thing as 2,361 in decimal. Okay. Uh-oh, just dropped my phone. Anybody with a question on that? Okay, no questions. So now I'm going to give you one of each to do real quick, and then we will move on to hex to binary and binary to hex, because those are super duper easy, just like octal. Okay, so go ahead and do these on your own. I want you to go from, and again, I'll make these a little bit more straightforward. How about 3F, and I want you to take that to decimal, and take, just take a nice round number like 400 and convert that into hex. Okay? Go ahead and do that real quick. Okay. $63. Steve still, hopefully you're not typing while you're driving. $63. is good. And so then for the next one, we've got, we just need the 2 digits, right? We need to do 16 to the 0 and 16 to the first. So 16 and 1. So 16 goes into 400. How many whole times? My trusty calculator. 400 divided by 16 equals 25. Oh my goodness, right on the nut. Look at that. So it goes in 25 times exactly. Wait a minute. What am I doing here? I need to go up to the next one, don't I? 25 times. Come on, John. Jeepers. So we got to go one more here. And 16 squared is 256. There we go. 256 goes into 400 one time. One whole time, I should say. And so we are left with 441. So 144. So 400 minus 256. I always double check myself. $144. Okay. So then how many times does 16 go into 144? Well, 144 divided by 16 equals 9. 9 on the nut. And then, so that means that this is 144 and leaves us with 0, and so this goes in 0 times. So this is, that was a good example. I like that. So 190 in hex is the same thing as 400 in decimal. Okay? All right. Very good. All right, so let's go ahead and move on to the next part here. And that is going to be, I think they even say something about it down here. And again, the successive division, the multiplying by weight, okay? And so actually I'm going to go back to the board and do the last 2 things, and then you guys will be free to go, okay? So this has gone really well. And again, this is on demand. The same link that I use for, when we go live here is the same link that it uses to make it permanent. So you can just click on this same link. And plus, I'm going to put this in a playlist on my channel. If you subscribe to my channel, that's the only way to see the playlists. But I'm like I said, I'm trying to keep everything away from the public as much as possible, but still be accessible. So, it's all unlisted. So you have to go through the playlist to find this stuff. Okay? So now we're going to go from hex to binary. And I'm going to use 101 or 1001, 100. I'm not going the right way. I got to start in the other one. How about 4C7? Okay? This all you got to do is go back to the, if I can get it pulled up here, go back to the chart. And you see here we're going to do direct conversion. This is the table that I'm referring to, but I'm not going to reference it until next time, even though I'm referencing it right now. Here you have all the binary, all the decimal, all the octal, all the hexadecimal, and then it even puts in the BC, which we'll talk about next time. But anyway, the hexadecimal is on here. So you're doing a direct conversion between these two for each digit. Okay? So what is, and now this one is 4 digits. Okay? Whereas octal is 3 digits of binary, this is 4 digits. Okay? So what's the 4-bit binary representation of 4? It's 0, 1, 0, 0. What's the 4-bit representation of C? Okay? C is going to be ED, so it's going to be, see, now I got to look. I don't have that one off the top of my head. It is 1, 0, it is 1, 1, 0, 0. Sorry about that. Yeah, 8 plus 4 is 12. So the next digits are 1, 1, 0, 0. The 4-bit representation of 7 is 0, 1, 1, 1. There you go. Okay, you don't even need that leading 0 out in front. So 4C7 in hex is the same thing as 100, 11, 000, 111 in binary. Okay? What if you want to go the other way? So if we want to go from binary to hex, and how about 1 0 1 1 0 1 0 1 1 1 0 1 1 1 1 1 base 2. Okay, we're going to do the same thing, only now we're going to group in groups of 4. Okay, so I start with the least significant bit. Here's a group of 4. Here's another group of 4. Here's another group of 4. Well, that was nice. I gave us the right amount. Okay, so what is 1011? 1011 is 11. Okay, and so 11 is the letter B. Okay, 0101. Okay, so this is where we're at. Okay, so 0101, the next one, that is the number 5, or the alphanumeric character 5. Okay, what about 1101? 1101 is D. Okay, so there you can see 1101 is D, and then 1111, that is the letter F. Okay, so this long string of binary converts to B5DF in hex. Okay, now I'm going to have you do 2 more, and we'll be free to go. So up here, I want you to do let's do a different one. How about CD? And I want you to convert that into binary. And then I want you to do 10101 11 1011 in binary, and I want you to convert that to hex. Okay, let's go ahead. So that's CD in hexadecimal, and I want you to convert that to binary, and then 111 001 1011, convert that into hex. Okay, so 1100 1101. And 39B. Okay, let's see what happens here. So the C is going to be directly converted from this chart. And so letter C is 1100. So that's 1100. That's the 4-bit representation of it. D is the next one. It's 1101. Okay, so I think that's what he had. Yep, that's what he had. So let's look at the next one now. So I'm going to start over here, and I'm going to group groups of 4 and groups of 4. And then to make a group of 4, I need these leading zeros here. But if we go look at our chart, 0011 is the number 3. 1001 is 9. And 1011 is the letter B. So this is 39B in hex. Okay, and I think that's what he had for both. Oh boy. Very good. All right. Any other questions? Got it typed out there. Any other questions? I'm about to jump over to Canvas and unleash the first quiz, and also point you to the lab for the week, which is not really a lab like you think. It's a worksheet of all these conversions, okay? So, if I don't see any questions, which I don't, let me get back over to the website. Okay. And so the quiz over Chapter 1, which we're going to finish Chapter 1 next week, but I'm at least going to get this. Well, you know what? I keep thinking in terms of weeks, right? We're not doing weeks. We're doing sessions, and we're having 2 weeks essentially in 1 week. So I'm going to wait until we meet on Thursday. So I'll wait till Thursday afternoon when we're done to release Quiz 1, okay? I don't want to get too far ahead of myself, I guess. But if you want to look at the lab, if we go to the modules, okay, this Lab 1, Numbers and Exercises, that one I am going to set a due date on. Okay, and so I'm going to come in here and edit. Now, today is the 9th. I'm going to give you until Sunday night to get this done, which you'll probably get it done in about half an hour if you're really meticulous. Okay, so this is going to be due this Sunday night at midnight, so the 14th. Okay, so here's the document. This is a 2-page lab document. I assume that nobody has a printer, okay? So here's what I would like for you to do. Let me go ahead and I'm going to open that up here in a second, but let me say this is a 2-page lab document. Please have all work and answers on another sheet. Take pictures of each page and upload the pictures. Okay? That's been the best way I've found to do this, because when you upload a picture, I have a tool that when I'm grading it allows me to underline things and highlight things, and I can point out where you've made a mistake. Okay? And so that's probably the easiest way to do this. So just do it on a separate piece of paper, have the document pulled up, and then so you're probably going to have 1 or 2 pages, which means you'll have 1 or 2 pictures. I'm not going to tell you how many pictures, however many it takes for you to show me all your work, okay? Now here's the thing, and I'm gonna go ahead and set that and save it, and then I'm going to turn right around. If I can come back to the announcement here. Where did I stick it? Maybe I didn't stick it up here. I did not. Okay. So, if I go to Google Play Store, and I search for binary number converter, okay? Every nerdy engineer that knows how to write an app can write one of these. Okay, and so there are so many at this point. I tried to keep up at one time, and there's just, I don't know. I have no idea which ones are good and which ones are bad. But there's, who knows how many of them there are. There are apps that will convert directly, okay, from one system to another. I'm not looking to see if you can use one of these apps. And I'm not looking to see if you can use the calculator on your laptop, because it has a converter too, and I'm going to show you that here in a second. But these exist, and I want you to put one on your phone because I want it to be something that you use to double check your answers. So look at the reviews on these. I mean, it's not like, I don't even know which ones I own here. Apparently I've downloaded this one before, but there's another one that I have in my apps. Oh, geez. I would know it if I saw it. It says 0101 in black on the front. See, it's not one of the newer ones, so it's probably buried down here. Yeah, see, this is still all the same type of stuff. Oh, there it is. There it is. Mine's made by Ruben Dougal. And I like it because it was one that I tried out a couple years ago, and it works, does everything I want it to do. So that's what I went with. So if you want to use the one I have, this is it. Okay, and this will also do two's complement, which means nothing to you now, but it certainly will at some point. All right. So that's the app I use. It'll do your conversions for you. So once again, in your assignment to me from the lab, I do not want just an answer sheet of the answers, because I just pointed you to the app. I want to see the work done, okay? That's going to help me feel better about you using the app in the future, because I will see that you did the work that was required, okay? So once again, I'm going to come back to the module here, and I'm going to go to that Lab 1, Numbers and Exercises, and I'll pull it up. Let me get rid of the syllabus back here, and pull this thing up. And then point my OBS to the Word document as it loads. Okay, so this is the lab, and normally in class I would print this out for you and all that good stuff. It's just the front and the back, okay? And so the first part here, I'm going to zoom out so you can see it. Okay. This is basically just copying all the stuff from that chart, okay? You're doing binary and hex for these decimal equivalents. So you're going to fill that table out, and then you're going to come over here, and here's a decimal column, here's a binary column, here's a hexadecimal column. And so you're given one of the three in each case, so read this left to right. That's a row, that's a row. So you do a row at a time here. And in each one, I've given you one of the three, and then you have to convert to the other two. And so this is where I need to see your work. I don't need to see work for this, but I want you to go through the exercise of writing it out. This one I do need to see your work on. Okay, I mean, it's only 1, 2, 3, 4, 5, 6, 7, 8, 9. There's only 9 of these. Okay, and you see how quick we just did them. And you know, these two columns right here, these are super easy to go between. Okay, now the other thing I want to point out is at the top of this, says, well, geez, that needs to be changed, doesn't it? Log on to Canvas. Geez, Blackboard was years ago. And click Class Sessions. Ours is the modules. Might as well just go ahead and do this now and save it, and then I'll re-upload it. Modules button, copy and paste the link from Session 1 into the browser window. And so this is what it is. If I go to this Whisk Online, okay, I just followed it, and I'm going to go back over here. It opens up, and what it has is, if I go to the digital link over here, it's got these different little games that you can play. Okay, digital number systems. Let's look at this one. Here's a game that does, let's see, drill from converting binary numbers to decimal numbers. So get in here and play around with these different little, they're essentially games. How quickly can you convert between them? I told you that you're going to get really good with, you know, with the numbers, and you'll be able to say, okay, 111, that's a 7. I know that just by looking at it. Okay, so basic concepts. There's a bunch of great stuff here. This probably won't do you much good for right now, but I want you to focus on this part of it. Okay, where it says digital number systems. All right, this is something for free that they've put online. It was really nice of them to do so. All right, but I want you to go through these, and that is at the top of that Word document there. Okay, so you can see here, do the binary to decimal, the drill for converting binary numbers, the hexadecimal number conversion, and the binary coded. I'm not going to know if you did this or not. Okay, that one's kind of on the honor system, but there's no reason why you wouldn't want to do that, because all it's going to do is make this stuff seem like it's going to demystify it. And you'll start thinking in terms of binary and hex. You'll start thinking in terms of octal. You know, obviously I don't have an octal section here, but that's because we really just use binary and hex. And so that's what I try to focus on. But I still think it's important that you know the octal as well. It's just that in this particular lab, there's no conversion. In the next lab, there is. Okay? So, any questions from that? Let me come back over here to... David asks, can we print and scan? Yes. You may print and scan. I'm giving you the other option because I'm going under the assumption that you do not have a printer, and then, you know, conversely, you also do not have a scanner. But if you do, absolutely, go ahead and print it out and then scan it back in, okay? If you do not have a printer, just have it up and then, you know, kind of like if you were doing homework on paper, okay? Do the assignment on paper, take pictures of it, and then upload it. That could be 2 pictures, that could be 3 pictures, whatever it is. Okay? Any other questions? So again, get the board. We'll talk about the last half of Chapter 1 next time, and then we'll go into Chapter 2. And I apologize, we went for 3 hours today. It won't usually happen like this. Like I said, I try not to talk any longer than 1 hour and 15 minutes usually. So, anyway, yeah, I guess if nobody has any other questions, you are all free to leave, and I will see you on Thursday.